And this is Sherri Sparks. We're going to be presenting a topic we call Shadow Walker. It's a new tool in order to hide your rootkit in memory. Some in the audience will have a little bit of review here at the beginning, may not know what a rootkit is. So one of the defining characteristics of a rootkit that separates it from the virus world and other type of malware is that a rootkit is there to provide stealth. It's there to hide you. Viruses mainly are there to reproduce themselves. Greg Hoagland, the founder of rootkit.com, defines a rootkit as a set of programs which patch or trojanize existing execution paths. You can see him later after this talk at the book signing. So what is a rootkit used for? A hacker could use it to conceal their presence. Once an attacker gains access to the box using their 0-day or whatever, they don't want to use the same technique over and over again to get access to the machine. Therefore, they install the rootkit. Rootkit will hide what actions that attacker is taking on the box, and it will also provide them future access with like a backdoor system, whatnot. However, rootkits also have a lawful purpose. The FBI or other agencies may use a rootkit as a sneak and peek, or for a legitimately executed search warrant. You can probably ask Michael Lynn about this afterwards. There's also Fortune 500 companies might want to use a rootkit in order to monitor their employees to enforce their IT policies within the organization. This does happen. So there's two different types of rootkits. There's mainly the user land rootkit and the kernel land rootkit. These correspond to the two layers that are used by operating systems within the Intel architecture. Your operating system, regardless of if it's Linux or if it's Windows, will use only two layers. Ring 0 is for the kernel mode rootkits. All kernel code, regardless of whether Microsoft produces the drivers or whether you cooked it up in your basement, runs at ring 0. Ring 3 is for user land processes. These processes are restricted into what they can do within memory and even what opcodes they can execute. So rootkits in the operating system. The operating system basically provides a well-documented API to upper-level user programs in order that the user land programs can access information that's within the kernel. So a user land process can say, hey, I need to access the disk drive, so I'll ask the kernel to do that for me. Also, the operating system provides a lower-level API between the hardware and itself. So if a rootkit is installed in ring 0, it's down in the kernel. It can also act as a middleman, just like the operating system is behaving. These are some of the different components that a rootkit may want to attack. We won't go into all of how you would do this and so forth, but just cover the main topics. A rootkit might want to attack a I/O manager in order to sniff keystrokes. So every time a key is depressed, it flows through the kernel. It goes through the I/O manager, and you would receive that notification. Device and file system drivers, you could attack these device drivers within the kernel in order to hide files. Your object manager, it's in the kernel. It maintains a list of all the objects within the system. Objects are used to do bookkeeping, so it could all your processes, all your thread objects are there within the object manager. Security reference monitor, you can make a couple byte patch to the security reference monitor within the kernel and turn off all ACLs. So regardless of where the request is coming from to access a particular object, it will succeed. And this was written up, I think, by Greg in FRAC 52. Process and thread manager, again, hide processes and threads. Configuration manager, you could attack that in order to hide registry keys. So the first generation of rootkits, they were extremely simple. They've been around for years and years. They replaced core pieces of the operating system on the file system. So maybe the Unix login program, the PS, the LS. They're so old that they're mainly first generation were just Unix variants, and we don't have probably a lot of examples of first gen Windows server examples. Second generation rootkits. These modified static OS components. So there's a lot of tables that the OS needs in order to jump to its relevant function. There's the system call table, represented here by the SSDT. There's the interrupt descriptor table, the IDT. Those are in kernel land, in user land, in your PE file. When you import a function from another library, that function address goes in your IAT for import address table. When you load a library that exports functions, that's held within that library's EAT, or export address table. There's also inline function hooking you can do where you don't patch the tables, you patch the functions directly. And these are different. You can do IAT hooking and EAT hooking from user mode, whereas kernel mode, you can hook all those things. Third generation rootkits modified the data structures that the operating system was using in order to keep counting information. So I term this DCOM, direct kernel object manipulation. If you reverse engineer the structures that the kernel uses and you understand them as much as the kernel does, since you're in kernel memory to begin with, you can just modify whatever bytes are there. The advantage of this is that you don't have to go through any API, so you can never be stopped from this. Kernel objects represent just about everything. Like we said, processes, threads. There's a kernel object for every driver loaded, security tokens, etc. So really quickly, the FU rootkit that is on rootkit.com that you can download, I wrote about 2 years ago. It's relatively stale right now, but the general premise still holds that you can hide a process within the system from like task manager, etc., just by modifying the linked list of processes. So here on the slide, if you want to hide the current process, which is the one in the middle, you could change its neighbors to point around it. You'll still get scheduled because scheduling is done at the thread level within the kernel and not the process level. However, Microsoft is reporting to you the number of processes not based upon the number of threads in the system, but upon the eProcess blocks. So there are several different ways to detect a rootkit, or methodologies. There's behavioral detection, integrity detection, signature-based, and more recently there's diff-based detection. And we'll have, here's some examples of these different methods in use. Signatures are basically AV scanners. Integrity checkers, their example of that is like Tripwire. Difference-based approaches are going to compare an upper level API call, like give me the list of files, to a very low level like disk scan. If you compare the two and there's a difference, you obviously have a rootkit. The different tools that do this currently are Microsoft Strider Ghostbuster, System Internal's Rootkit Revealer, and F-Secure Blacklight. So what is behavioral detection? Well, it looks for the effects of the rootkit within memory, within memory, and one of the things it may be looking for is diverted execution paths. So I wrote this tool called Vice that will look for hooks within all those different static locations within the kernel and within PE files. Also, Joanna Rakowska pioneered a methodology, the tool is called Patch Finder, where she counts the number of instructions when a system call is made on a clean box. Then she does it at a later point in time, compares the difference. If a large number of additional instructions were executed, then you know that you've been hooked. Another behavioral methodology might be to detect the number, order, or frequency of system calls. So every program should have some type of system call signature. So maybe open files called, then read file, then read file, then read file, then close file. So if you found deviations in that set of instructions or the order of those system calls, then you probably have some additional code running that wasn't in the original process. The problems with these techniques is they suffer from a high level of false positives. It's really hard for the user to determine if it's truly malicious or not. Integrity checking, this is simple, it's been around forever. Just does CRC checks or some kind of secure cryptographic non-colliding hash function on OS components. This could be disk or it could be memory. However, most products out there just do disk. So you calculate a known good value, compare it later, see what happened. If they don't agree, then you know that the file's been changed. Signature-based detection is the tried and true way of antivirus software. It's been around for quite a while. It searches memory for, or searches memory or file system for patterns. Again, this is mostly the file system. It's looking for a specific ordering of opcodes that are defined by, or that are used by viral code. This is really accurate, unless you came to the last talk maybe and you can defeat the AV product. However, it only detects known patterns. So if you start modifying your code, you won't be detected. So, what's the motivations for this talk? Well, kernel rootkits are the most powerful type of rootkits there are. And there's some very, very sophisticated kernel rootkits. However, a simple scan of memory can find them. This is kind of lame. So kernel rootkits reside in non-page pool. So they're always there in memory. They're not going to be paged out. You can just start scanning memory to find them. So we need a way to hide the kernel rootkit within memory. So you could take the virus approach and use some kind of polymorphism into your code, into your rootkit code. However, this is kind of a level of sophistication that hasn't been seen within kernel rootkits. It's difficult. Also, there is like one public example I know of that uses a polymorphic technique, but you send the guy like 40 euro, he hand does it and sends it back to you, your new rootkit. So now, with no further ado, I'm going to introduce Sherri, and she's going to talk about Shadow Walker, the 4th generation of rootkits.
Thank you, Jamie. Hi, my name is Sherri Sparks. I'm going to be discussing the implementation of our Shadow Walker technology. Like Jamie mentioned, polymorphism is certainly a possibility for a rootkit to use to hide its code in memory. However, polymorphism, it's not necessarily the optimal approach for a rootkit. Not only does a rootkit need to hide its own code, it also needs to hide changes that it makes to operating system components. Ideally, I would like to defeat things like the memory-based version of Tripwire that would perhaps perform integrity checks upon the kernel image. So therefore, what we need is a better method than just polymorphism. And that method is going to, the alternative that we're going to present is going to be virtual memory subversion. Rootkits have basically, as Jamie said, compromised virtually all of the operating system subsystems. I mean, we have public kernel rootkits that compromise the I/O manager, the configuration manager, security reference monitor. However, the one subsystem that we have not seen an example of a public kernel rootkit to compromise is the memory subsystem. So basically what we're going to do today is to provide a proof of concept demonstration that a rootkit is capable of transparently controlling the contents of memory viewed by other applications, the operating system, and other kernel drivers. So basically what's going to happen is we are going to hook memory in such a way that even if you write a kernel driver that has an assembly routine that is using, assembly move instructions to read data, it's going to receive incorrect data if it tries to read the rootkit's code section. And one of the drawing cards to this technique is the fact that it exploits some features of the architecture which actually cause it to have almost no performance impact. Meaning that when this rootkit driver and the memory hook is installed, there is basically no performance impact that any user could notice. And clearly this will make it an attractive solution not only for rootkits but also for viruses and spyware and other types of malware. Okay, so what are the implications of virtual memory subversion? Well, you know, rootkit scanners are starting to get a little bit smarter. They're starting to realize they can't necessarily trust the API interface because, you know, obviously one of the most common methods of rootkits is API hooking. But the one thing and the one vulnerability that they do have is even if they don't trust the API interface, scanners intrinsically trust their view of memory. They trust that the memory reads they perform are actually returning them the data actually stored at that memory location. So therefore, if we can control a scanner's memory reads, we can fool signature scanners and potentially make a known rootkit, worm, or virus immune to an in-memory signature scan. We can also fool integrity checkers and other types of heuristic scanners which rely upon their ability to detect modifications. One example of that would be Vice, which attempts, for example, to detect inline hooks. Obviously, the beginning of a function body, it's relatively heuristically abnormal to have the beginning of your function body to start with a jump instruction, as opposed to the more traditional, you know, setting up the stack, allocating local variables type code. So basically, if we could fake a memory scanner's read, say, of some core operating system driver that we have hooked, then our code will execute, but the scanner will receive incorrect information. It won't see the hooked version, it will see a clean version. Since this technique primarily involves subversion of the virtual memory system, I know probably for most people it's been a while since they've had, you know, a computer science class in operating systems. So we're going to do a brief review of some of the virtual memory concepts. The first thing we're going to talk about the Windows virtual address space layout. Then we're going to talk about some of the more core concepts, paging and segmentation, page tables and PTEs, how virtual to physical address translation is carried out by the hardware, the role of the page fault handler, the paging performance problem, and then how that has been mitigated by hardware using the translation look-aside buffer, and then finally memory access types. This is just a simple example of the Windows virtual address space layouts. The most common address space layout divides the address space into user and kernel portions. Just like Jamie said, you know, we have user mode and kernel mode. Well, the memory layout kind of mirrors that. The lower 2 gigabytes of the virtual address space correspond to user mode memory. This is where your application code and, you know, regular user processes are going to reside. The upper 2 gigabytes are going to be where the operating system kernel itself is loaded, where other third-party drivers are loaded, and also where non-page pool and stuff like the process page tables are located. There is an alternative memory layout introduced in Windows Server 2003, which actually allows you to have a 3 gigabyte user address space and a 1 gigabyte address space for the system space. So what is virtual memory? What's the main idea? Basically, in virtual memory, we want to separate the virtual and physical address spaces. So basically, your virtual address space is going to be defined by the width of your address bus. So if we have a 32-bit system, we have the capability of addressing 2 to the 32, or approximately 4 gigabytes of contiguous memory. However, most of us don't have that much physical memory or RAM installed on our systems. So therefore, our physical address space is going to be constrained by the amount of RAM that we have, which means that most of the time, the virtual address space is going to be significantly larger than the physical address space. And the idea behind virtual memory is we want to manage the virtual and physical address spaces by dividing them into fixed size blocks. Under a paging scheme, all of these blocks are the same size. Under segmentation, these blocks may be variable sizes. Windows actually uses a combination of both segmentation and paging. However, the focus of our talk is mostly on the paging architecture. The operating system is what actually handles this mapping. There has to be some kind of information that performs a mapping or a translation between the virtual memory block and the physical memory block. And this is going to be handled by the operating system. Another interesting thing to note is that virtually contiguous memory blocks do not have to be physically contiguous. This is because the operating system handles that mapping information and can arbitrarily map a virtual block to basically any free physical block. This illustration just shows basically the concepts that I talked about a minute ago in the last slide for paging. We have our virtual address space, which is broken into the fixed size blocks called pages. We have our physical address space, which is broken into the same fixed size blocks. These are typically referred to as frames. And then we have some kind of a mapping relationship between the pages and the frames, which is what the operating system is managing. And as you can see clearly from the picture, virtually contiguous blocks are not necessarily physically contiguous. This mapping information is going to be stored in structures called page tables. And page tables themselves consist of a number of entries called page table entries, which contain status information for that particular page in memory. This illustrates the basic structure of an x86 page table entry for a 4 kilobyte page. Some of the more interesting bits in here are, for example, the valid bit. That's one of the most important bits. That's the bit that the operating system is going to use to determine if that page is actually resident in main memory or if it's been paged out to the disk and is sitting in the page file. We also have the write bit. That bit is significant in terms of protection. Is that page read-only, or can it also be written to? And then there's a number of other bits, like the cache disabled bit and the dirty bit, which the OS uses in its virtual memory management. And then the last bit that's kind of interesting from our perspective is the global bit. Basically, the hardware has a buffer called the translation look-aside buffer, which is a hardware cache for virtual to physical mapping information. And on a context switch, that has to be flushed, meaning we have to empty it. So basically, if you set the global bit, you can prevent that entry from being flushed from the translation look-aside buffer. And this is used as mostly a performance enhancement, because there's some pages that may never need to be flushed on a context switch, like part of the operating system kernel. Excuse me. The big picture here, I just created this little diagram. We have the user virtual address part of the space. We have the kernel space. In kernel space, we have the process page tables. And then those process page tables hold the PTE entries. And each PTE entry has the mapping information, which maps to a physical frame in memory. And of course, the most important part of the PTE is going to be the base physical address of the page frame in physical memory, which is also stored in the PTE in addition to all the status bits. So how do you actually index into these page tables? You have a given address. Well, how do you figure out which page table entry it corresponds to? As it ends up, that information is actually encoded into the virtual address. Virtual addresses are going to form indexes into page tables. Basically, your virtual address can kind of be divided into two parts. The first part is going to be the virtual page number, and the second part is going to be the byte index. The virtual page number is the part that is responsible for indexing into the page table. Page tables, there's a number of different schemes for page tables, but you can have a single level page table, or you can have a multi-level page table. As it ends up, the x86 uses a two-level paging structure, which means that it has not only page tables, but it has a page directory. And in practical terms, what that means is we have a page directory which whereas a normal page table contains pointers to physical frames in memory, our page directory actually contains pointers to page tables, and then the page tables contain pointers to the physical memory frames. And basically that also means that now we're able to actually page out the page tables as well. So basically the virtual page number under this two-level paging scheme, we have to divide it into a page directory index and a page table index. The upper 10 bits of the virtual address form the index into the page directory, while the middle 10 bits in the virtual address form the page table index. The byte index, in contrast, is going to be an offset into the actual physical frame. This slide gets a little complicated, but I'm going to do my best. Basically, when when virtual to physical address translation occurs at the hardware level, there's a series of steps that you have to go through. First of all, you have to locate the page directory. The page directory is actually a pointer to it is contained in the K process block, but also the hardware register CR3 control register contains the physical address of the current page directory. So once we've located the page directory, now we need to actually locate the actual page directory entry, which is going to contain a pointer to the page table in physical memory. So basically we take the base of the page directory and we extract the page directory index from the virtual address, and then we use that to locate the actual entry in the page directory. Now this entry is going to have a pointer to the base physical address of the page table. So now at this point we've located the page table. The page table index now is going to be combined with that base pointer to locate the actual page table entry. The page table entry now has the base physical address of the actual physical frame, which is going to contain the data. So now we're at the base address of the frame in physical memory. But to actually get to the address that caused the memory access, we now need to combine it with the byte index or offset into that page frame. And therefore you get your complete physical address and your translation is complete. Like we mentioned earlier, physical memory may be smaller than the virtual address space. And in practical terms, what that means is that we may run out of physical frames. And that means that the operating system may need to move less recently used pages out to the page file to satisfy current memory demands. So basically when the OS has to move a page from main memory out to the page file, what it does is it marks its PTE as invalid. So that page is now invalid. It's no longer present in main memory. Once it does that, it will copy it out to the disk, and it may or may not need to bring in a new page, and then it will, and then whenever an access occurs, it will cause a page fault. And the page fault will cause invocation of the page fault handler, which is the int0e handler. And this is going to be the most common cause of a page fault. It's going to be attempting to access a page that has been swapped out to the page file. There's a little caveat here, because an attempted access to a virtual address whose PTE is marked non-present is going to generate a page fault if and only if the translation is not cached in the TLB, which is the hardware cache. The TLB is going to be first on the memory access path, even before the page tables. So if it's present in the TLB, the memory access will be resolved from the TLB, and it will never go out to the page tables and generate a page fault. This is going to become important later on. The other reason we can have page faults is for memory protection violations. For example, user mode code that is trying to access kernel memory will cause a page fault. An attempt to write to memory that is marked read-only with write protection enabled will cause a page fault. And if in case my last slide on that virtual to physical translation was a little confusing or lost some of you, I have this slide which shows kind of a high-level overview on the memory access path when a page fault occurs. So basically, first thing, we have a memory access. So we go out to the page directory. We want to look up the page table. In this case, it's present. So now the page table can be accessed. Well, in this case, the actual, the PTE is marked invalid or not present. It's going to cause a page fault. This is going to cause an interrupt, which is going to invoke the page fault handler. Now, the normal role of the operating system page fault handler is it's going to go out to the disk and it's going to locate that page, which presumably is not present in main memory right now, and it's going to copy it into memory. And then, of course, it's going to mark that PTE as being valid now. Unfortunately, some people would say that originally paging really wasn't that great of an idea. And the reason is because paging, or virtual memory in general, incurs quite a steep performance hit. If you think back to our last slide, really on a memory access, we really have 3 memory accesses. In the best case, we have to access the page directory, we have to access the page table, and then we have to access the offset. So one memory access actually requires 3 memory accesses, which obviously is going to cause significant degradation of performance. That's, of course, the best case. In the worst case, we have those 3 memory accesses plus potentially 2 disk IOs, because it's possible that the page table itself could be paged out because we're dealing with a 2-level paging scheme, and then the actual the page frame itself may be paged out. So we could end up with 2 disk IOs, which of course are going to be the most costly operation. So basically, hardware designers developed a solution that helps to mitigate this intrinsic problem with paging, and that solution was the translation look-aside buffer. The TLB is a high-speed cache of virtual to physical address mappings that are frequently used. The TLB is typically implemented in associative memory. It's a lot smaller than main memory, but it's also a lot faster. So basically, this TLB now is your first step in the memory access path. On a memory access path, or on a memory access, the TLB will be searched first for the virtual to physical translation before you ever go out to the page tables. If it's actually found in the TLB, it will be termed a hit. If it's not found, it'll be termed a miss, and it will be brought into the TLB. The x86 actually uses a split TLB architecture. It has an ITLB, which holds virtual to physical translations for executing code, and a DTLB, which holds the translations for data. It's important to note that modern TLBs actually have extremely high hit rates, and they seldom incur the performance of a page table walk. This is just a simple example of the translation look-aside buffer on a memory access. Basically, the TLB has 2 parts. It has a tag portion and a data portion in the cache. And the virtual page number from the virtual address is extracted and compared with the tag, which is going to be the virtual page number stored in the TLB. And all of these, depending upon the associativity, it's going to be searched in parallel very rapidly. And if it finds it, it's going to report a hit, and then it will send back the corresponding physical frame that corresponds to that virtual page number. So this is just a little animation that shows the memory access path with a TLB. And I show the split memory access path like the Intel architecture has. So basically, the memory access occurs. Well, in this case, that's going to be a code access. We have virtual page number of 12. So we go out to the ITLB. The ITLB is searched. It locates the corresponding entry for virtual page number 12, and now we have the frame information. And we can go directly out to physical memory, and we know the base address of the physical frame. We totally bypass, in this case, the page directory and the page tables, which, of course, the TLB is going to be a whole lot faster than trying to access the page tables. Now, we might not be so lucky because, like I said, the TLB is kind of small, and it's possible that you could have had like a cache line eviction, which means that your entry is no longer present in the TLB, even if it was at one point. So in this case, you're going to get a TLB miss. So here's our memory access, another code access. We go out to the ITLB, it's not there, so we get a miss. Well, this means now we have to go out to the page tables and try to resolve it. Oops, something's not there that we need, so it's going to cause a page fault. So now that we have a page fault, we know what happens. The int0e handler is going to be invoked, which is going to run, and it's going to go out to the disk and bring that frame in from the page file and load it into physical memory. And then, of course, mark the page table entry as present. We have three basic memory access types that I'm sure everyone is familiar with. We have read, write, and execute access. One thing that's kind of interesting is under the Intel architecture, we really don't have discrete read, write, and execute access. We actually have only two access types. We have read execute access and read write execute access. Execute is basically implied. That means that all memory is intrinsically executable. In some cases, it may be advantageous to actually be able to differentiate between, say, execute and read write. One such application would be the application of non-executable memory and used in buffer overflow protection. For example, the stack typically is going to store data. The stack normally doesn't store code, executing code, unless you have a buffer overflow attack in progress and shell code is executing. So therefore, it stands to reason it would be nice to be able to mark our stack as being non-executable. Unfortunately, because of the Intel memory semantics of having implied executability, there's no way to actually easily do that. Well, the PAX project actually attempted to implement this read-write no execute memory using strictly software, since there was no hardware support for it. And they succeeded. Windows XP Service Pack 2 and Server 2003 Service Pack 1 subsequently added its own version of OS software support for non-executable memory. And this is termed DEP, or Data Execution Prevention. As a side note, hardware support for non-executable memory has been added to some processors, including 64-bit processors and the Pentium 4. Well, now starts our little bit of our talk about how this thing is going to work. We've established that PAX created this non-executable memory using a software implementation. Well, what we want to do now is to take an offensive spin on this defensive PAX technology, kind of pervert it to a certain extent. We want to do the inverse of PAX. That is, we want, as a rootkit, we want to hide our code. Therefore, we also want to differentiate between execute and read-write accesses. I mean, we obviously want our rootkit code to run, but we don't want a scanner to be able to read and write it. So therefore, we would say that read accesses of the code section of a rootkit driver would most likely indicate the presence of a scanner. So therefore, what we want is we want actually to have execute, but no read-write, or should I say diverted read-write. We want the scanner to actually see something different than what's actually there. So there's several implementation issues. These are kind of the three primary implementational issues. We need a way first to filter execute and read-write accesses. Once we have a way to filter them, now we need a way to fake the read-write memory accesses once they're detected. And once we fake them, all this is for naught if we kill our system performance. So we need to ensure that our performance is not adversely affected. So in order to differentiate between execute and read-write, basically we want to trap accesses to a certain range of memory or certain page. We saw that we can generate page faults using by either marking the page as non-present or playing with memory protection. and then of course hooking the page fault handler to handle the subsequent faults. In our case, we're going to be hiding kernel pages, so we opted to use the non-present bit. So basically we can mark the page non-present, and even though it is actually indeed present, and then whenever an access occurs to that page, it will generate a page fault, which is trapped and routed to a new page fault handler. Now, as far as differentiating between executes and read-writes, that's actually relatively simple in the page fault handler. And that's because once we enter the page fault handler, we have the saved instruction pointer and we have the faulting address. So if we compare the instruction pointer to the faulting address and they match, then we can conclude it's an execute access. If they don't match, we can conclude it's a read-write. One interesting note that we need to make is that this new page fault handler has to run with the operating system. So it has to, it can't crash the system, it can't interfere with normal virtual memory handling that the operating system would be doing. So therefore, we have to have some mechanism of differentiating our page faults from the hidden rootkit driver from the page faults resulting from normal paging activity that the operating system is managing. So therefore, we make two constraints on this. First, the pages must be in non-paged memory. If they're in non-paged memory and we receive a page fault on them, we're guaranteed that that page would never have been swapped out to the page file. So we don't have to worry about worrying if it's in the page file or trying to bring it back in or anything like that. The other alternative would be to have pageable memory and to lock it down. The OS provides a couple APIs which can lock a range of memory down. Now, once we've actually differentiated between the execute and the read-write, now we want to actually fake them. So we want the executes to execute, for example, the rootkit code. If a scanner comes along and tries to read that memory range, we want it to see something totally different, obviously not the rootkit code. So basically what we're going to do is we're going to exploit a feature of the architecture. And this is basically the inversion of the implementation of the DEP or data execution prevention. Normally, we have the ITLB and the DTLB, as I said, which are going to hold the virtual to physical mapping information. It's going to cache it for frequently used pages. So under normal circumstances, the ITLB and the DTLB are going to have identical mapping information, meaning that, for example, for memory access with this virtual page number equals 12, the ITLB is going to have a mapping an entry that maps that to frame equals 2, and the DTLB is also going to have a mapping that the frame equals to 2. So the ITLB and the DTLB are both synchronized. They both point to the same frame in physical memory. Well, that's the normal situation. What if we could actually desynchronize them? So now our ITLB for code, now the frame it points to 2, but the DTLB now for VPN equals 12, now its mapping is frame equals 52. So you can speculate here that frame equals 2 for the executable code, that frame can hold the rootkit code, which is going to execute as normal. In contrast, the DTLB now is going to point to some frame which contains random garbage or something other than the rootkit code. So now when the rootkit is executing, it's going to receive the mapping from the ITLB, which points to the correct code, but when a scanner comes along and tries to access that memory, now its reads and writes get filtered through the DTLB, which is going to point to some other frame which contains random garbage. So the question is, how do you actually implement this? In theory, it sounds good if we can desynchronize the TLBs, but how do we actually do this? TLBs are mostly hardware controlled. There's not that much software control of the TLB, but there's a few mechanisms that you can use to indirectly control it. First of all, you can flush the TLB. There's at least 2 ways of flushing the TLB. You can either reload CR3, the control register, which is what happens on a context switch, and it causes all of the TLB entries to be flushed, except for the global ones. Or you can execute an invalidate page instruction, which causes a specific TLB entry to be flushed. So right now we have the capability to selectively flush the TLB. Now we need to selectively load it. Well, as it so happens, executing a data access instruction causes the DTLB to be loaded, but not the ITLB. Conversely, executing a call causes the ITLB to be loaded, but not the DTLB. So therefore, we can discretely load the two TLBs. So basically, our rootkit hiding technology called Shadow Walker, it consists of two components. It consists of a memory hook engine, which has code for instantiating the hook, which we're going to discuss how the hook is instantiated, and then it has a custom page fault handler. The second component is, of course, a modified foo rootkit, which is taken from Jamie's original foo rootkit. In order to install the memory hook, obviously we need to hook the page fault handler. In this case, this is going to be int 0e. So we're going to install our new page fault handler. And the theory is we're going to handle the page faults that are resulting from our hook pages, and we're going to selectively load the correct TLB such that we desynchronize them. And then the next step we're going to do is we're going to insert the page. Once the page fault handler is hooked, we're going to insert the page into a hash table of hooked pages. Because once we get in the page fault handler, we need to have optimized code. We need to be able to look it up as fast as possible and determine, is this fault for us or is it not? Is it an OS fault? If it's an OS fault, we need to hand it down to the operating system as fast as possible. So once we've established that, then we go ahead and mark the page not present. Now this means that subsequent accesses to that page are going to cause faults, which are going to invoke the new rootkit's page fault handler. The last step is really the most important here, because like I said, the TLB is first on the memory access path, meaning if we mark that page not present, and then the mapping is still present in the TLB, then the next time that range of memory is accessed, it will be pulled from the TLB without going out to the page tables and generating a page fault. So we would have lost control. So therefore, the last step finally is you have to flush the TLB. And this guarantees that the next time that range of memory is accessed, it's going to generate a page fault, which is going to call the rootkit page fault handler, which will selectively load up the hardware TLB. So the custom page fault handler, its primary task is to filter, read, write, and execute accesses for hooked pages. It's going to pass down the faults on unhooked pages to the OS page fault handler transparently. But if it does detect a page fault that's a result of the hook, it's going to manually load up the ITLB if it's an execute access, determines it's an execute, or it's going to manually load up the DTLB on a data access. Most memory references will in fact be resolved via the TLB path and will not cause page faults. However, there will be a few page faults, but not a significantly large number. Page faults will occur definitely on the first execute and data accesses to the page, because when we instantiated the hook, we had to flush the TLB, so there's no more mappings. Next time it will cause a page fault. On possibly TLB cache line evictions, like I said, there may be another page that maps to that position in the TLB cache, and the current one will have to be evicted. So on the next access, it will cause a page fault again, which will then reload the TLB. And then, of course, lastly, on an explicit TLB flush, a context switch if the global bit is not enabled. This is kind of just a really simple pseudocode for the page fault handler, for the basic functionality, for enforcing execute diverted read-write semantics on kernel pages. We're not dealing with user pages right now, just for simplicity and tracking context and stuff like that. So basically, on entry into the page fault handler, the first thing we can do for efficiency is, if it's not our fault, we're going to pass it down as fast as possible. So we check if the processor's in user mode. If it is in user mode, we want to just pass it to the OS, because we don't handle user mode stuff. If the faulting address is a user page, then we're also going to pass it down. We don't handle user pages right now. Now, in contrast, if the faulty address is from a hidden page, then we're going to do one of two things. We're going to determine if it's a code access or if it's a data access. If it's a code access, we're going to go over and we're going to manually load up the ITLB. If it's a data access, we're going to go over and manually load up the DTLB. So if it's an instruction, if it's an actual execute, we're loading the ITLB. So basically we want that PTE to contain the physical frame address of the physical frame that contains the rootkit code. So we can replace the frame with the one that is going to point to the rootkit code. Now, in order to let that memory access go through, we have to temporarily mark that PTE as present. Once we do that, we will execute a call into that page. And that's one thing I neglected to mention in the initialization, is that we need to have a means of calling into that page, which in the case, for example, if you're hiding a section in a PE file, a lot of times you'll have alignment requirements and you'll have some empty space, say, at the end of a section. Well, all you need to do is just take one byte and patch in a return. So basically it calls into a return that's been patched into that page. And then, of course, the faulty address is marked not present again before we exit the page fault handler. We replace the old frame and then return without passing down to the OS. The OS doesn't need to know anything about this particular page fault. If it was a data access, then we're going to load the DTLB, and this is very straightforward. We're going to mark it present. We're going to execute. We're going to explicitly execute, like say, a move instruction, a data read, and then we're going to mark it not present again. And once again, we're going to pass down control back to the faulting code without passing it down to the OS. So this is all about executable code hiding. So what about data hiding? Well, the thing that makes it so elegant about the code hiding is the fact that we can desynchronize these two TLBs, which means that we can make full use of the hardware cache and the performance capabilities that are already built into the architecture. If for data hiding, we actually have to keep the DTLB empty, because for some instances for some data reads, for example, if our rootkit wants to read its own data, then it needs to see a different mapping than if, say, a scanner wants to read our data. So therefore, since we only have one DTLB, it's going to have to be kept empty. And basically, in practical terms, what this means is it's going to cause one page fault per data access. And that's obviously going to hit the performance a bit. Of course, for the memory access to go through in the page fault handler, it doesn't mean that we can't filter the data accesses. But and the DTLB must be loaded with the correct mapping, or it will be loaded when that memory access goes through. But the problem is now that it's loaded, now in order to maintain control, we're going to have to flush it after the memory access. So really there's two solutions to this, one a bit more elegant than the other. We can have possibly a protocol-based approach between the driver and the page fault handler. This is where the driver explicitly flushes the TLB before and after making data references to data pages that are hidden. Or we can use a debugging approach where we actually have kind of a rudimentary kernel debugger that sets up the single step and does a flush after that instruction that performed the memory access has been stepped. Right now, our proof of concept, we have the protocol-based approach implemented just to see if it would work, but the debugging approach is, of course, a lot more flexible and less cumbersome on the part of the driver. Our modified FU rootkit, that's the object that we're hiding. It runs as a system thread. It's purely kernel mode. It scans the active process list looking for processes named _FU_, and then it unlinks them if it finds them. That's really all it does. It's not really an attack tool per se. It has no dependence on user land initialization, no symbolic link, no functional device, and it's really designed as an in-memory rootkit. I mean, if we have this driver just sitting around on the file system, clearly we defeat the purpose of this stealth, because it's a sitting duck now for file system scans, and we have opened up a whole new can of worms. So rather, we kind of envision this as something that would be installed via maybe a kernel exploit. And as such, then we would evade the disk detection. And that's not such an unreasonable thought when you consider that, probably this would be exploiting some kind of a server system. And, server systems aren't rebooted that often, so there's a good chance that our rootkit would remain around for a while. Now, lastly, the impact on system performance. Modern TLBs, like I said, they have really high hit rates. So therefore, the translations, even though intuitively speaking, we're marking pages not present, we would expect that all these extra page faults are going to start hitting our performance. But actually, that's not the case. Because, like I said, TLB is first on the memory access path. Almost all the translations are going to go through the TLB, just like normal, with maybe just a few extra page faults. So therefore, using this, the memory hook engine to hide the rootkit driver has subjectively no noticeable performance impact. Now, this is probably partly, in fact, due to the fact that we're hiding a driver. How many pages are we hiding? Like maybe 4 or 5 pages. Obviously, performance might become more of an issue if you were hiding lots and lots of pages, because your TLB can only hold a certain number of translations, and you're going to start running into evictions and collisions and generating a whole lot more page faults. But for hiding a few drivers or a handful of pages, there is basically no performance impact noticeable. As this is not really a weaponized attack tool, there are a number of known limitations, which we may work to remedy some of these in the future. But right now, this is strictly proof of concept. First, there's no PAE support. PAE tries to extend the addressing from 32 to 36 bits. Secondly, there is no hyper-threading or multiprocessor support. If you try to run this code under a hyper-threaded system, it will crash and burn. Currently, it hides only 4 kilobyte size kernel pages. We have the capability to hide the 4 megabyte pages, of course, but the main 4 megabyte page of interest is the page where NTOS kernel sits. And unfortunately, NTOS kernel, that page has a bunch of stuff like interrupt handlers and the OS page fault handler, and there happens to be some current technical issues with getting it to actually work stably. Now, just a little bit about detection before we do our demo. First of all, just speaking from the most simple perspective, heuristically, we made the constraint because we have to differentiate between the page faults resulting from our memory hook and normal OS page faults. So we said, okay, well, these pages have to be non-paged or they have to be locked down. Well, right now it's a driver sit in non-paged memory, so these are non-paged pages that are marked not present. Obviously, this is kind of heuristically abnormal. I mean, you've got pages that aren't there in non-paged memory. The OS wouldn't do that. Whether or not that's a sufficient heuristic to say that a rootkit is on there, pretty debatable. But it's still a little weird. Also, there's also some other issues and weaknesses. The page fault handler code itself cannot be concealed using this technique because that would imply that we have to mark the page containing the page fault handler not present. Obviously, marking the page fault handler page not present kind of introduces some recursive issues, and it's not a viable solution. So therefore, we have to fall back on more traditional mechanisms. In this particular case, since the page fault handler is it's small, it's fairly small, it's written totally in assembly, no API calls in there. We can say that a reasonable solution would be to implement viral polymorphism on the page fault handler. Next, it's difficult to conceal the hooks on the IDT. A number of mechanisms have been proposed for hiding IDT hooks, including using like the debug registers, but none of these are really particularly effective. And one huge drawback, which actually even Shadow Walker will be kind of victim to, is the fact that this is hooking virtual memory. It's not hooking physical memory. Debug registers also hook virtual memory. So in practical terms, what that means is that you have basically you can take a given physical frame and you can remap it to a new virtual address, and then you can read the data contents. So if you access it through one virtual address, it generates a page fault or it generates a debug exception, and you get your fake data. But if you access it through through a new virtual address where you would remap it, then potentially you might be able to use some kind of a diff-based approach. So concealing the IDT hooks for that reason can be problematic, because you could do this little remapping trick on the IDT where you might use the SIDT instruction to get the original address, and then you could remap to a new virtual address, and then be able to detect differences between the IDTs. Obviously, unfortunately, there's not really a good solution to protect against this remapping. Fortunately, I guess, or unfortunately, as the case may be, most scanners are fairly primitive right now, I think, and typically tend to do virtual memory scans. And basically, the point is that virtual memory scans are inadequate. Just like now you can't assume that the API, the kernel or the user API, is not compromised. Well, now you can't assume that virtual memory is not compromised either. So therefore, more advanced scanners are going to have to totally revamp their way of scanning and base it on like remapping. And then lastly, of course, really the best solution would be a hardware memory scanner. Some kind of a hardware scanner that has direct access to the memory bus that can read physical memory without having to go through the paging system at all. And of course, we end up with our yin and yang, and I'll make this brief because I want to give the demo. There are actually, here we're illustrating the offensive, it's Black Hat, but there's also defensive applications for this, even for intrusion detection, AV, firewall drivers. Obviously, rootkits work by installing hooks, making modifications to binary code, which may include, say, firewall drivers or, or the driver for an antivirus. So basically, this kind of technology could be applied to, say, a firewall driver. So now your firewall driver, it executes, but now a rootkit comes along and now it wants to write to your firewall driver to install a hook. So now that is now diverted off to a shadow page where it has no effect. So the rootkit thinks that it's modified the firewall driver when in fact it has done nothing. So now I'm going to go ahead and show a little demo here, crossing my fingers. Okay, basically here I have this driver monitor program. Comes with Driver Studio. It loads a kernel driver. So what I'm going to do is I'm going to go ahead and load up. This is implemented as 2 drivers right now. I'm going to go ahead and load up msdirectx.sys, which is Jamie's FU rootkit driver. Okay, so the driver started successfully, and now I'm just going to step into soft ice here real quick, and I'm going to get the load address for the driver. Let me verify that. Okay, so I wrote just this little tiny dumping utility. So basically we're going to take a memory dump of this virtual address, which this user application communicates to the actual dump driver. It's going to go ahead and do a dump. And for everyone that's familiar with looking at hex dumps, you'll recognize this 4D, 5A in the first 2 bytes. That's going to be your MZ on the PE header. So basically right now we're looking at the PE header, the first few bytes of it, of Jamie's FU rootkit driver. So what we're going to do now is we're going to go ahead and now load up the memory hook driver. Okay, so that started successfully. So now we're going to take another memory dump of that exact same address, and now all we get is blanks. It looks like uninitialized memory. So basically what I've done is I'm just diverting all the read writes off to what looks like an uninitialized page. So, so now what we can do is we can go back and we can remove the hook. So now we're going to take another dump, and you'll see indeed that now it's unhidden again. Now we have our PE header back. And for all of you guys that are a little bit skeptical of my little dumper tool, thinking maybe I'm trying to pull the wool over your eyes, I'm going to do this demo again, but I'm going to do it in soft ice because I'm sure most people in here are pretty familiar with that tool. So basically I'm going to enter soft ice and I'm going to type mod msdirectx.sys, which is the rootkit driver. And so now I get the load address. And we're going to go ahead and display that memory. So, you know, just the standard, you know, MZ PE header sitting right there. So now we're going to exit soft ice. And now we're going to go ahead and install the hook again. Okay, well, let's execute the mod command again. And go ahead and display the base address of the driver. And soft ice, of course, anything that it handles all of its memory management itself. So if something appears like it's not present, it won't touch it. It just puts these little question marks in, which totally makes sense because right now those pages have been marked as not present. However, one thing that you can note that lets you definitely know that it's working is if you look down at the bottom where we have printed out the module information, you can see the PE header. Well, normally what soft ice does is it's going to take the base address of the module, and there's like an offset, and it's going to get the address of the PE header. Well, it's obviously having to read some data from within the header to get that. So as you can see here, the PE header is now 0, whereas previously, so soft ice is getting fake too. So previously, if we unload this, and then we execute the mod command again, well, now we have the PE header address back again. So now I'll just go ahead and unload the rootkit. And I'll field questions now, if you have any questions. Yes?
What would keep a memory reader from faking it up by pretending to ask for the memory to execute?
Please say that again.
What information allows you to make a decision whether it's read, write, or execute? And couldn't the process fake the execute bit so that you think it's for execution and you go ahead and get it relevant?
Instruction.
What?
It's a type of instruction that decides that.
The question is, what is it that allows you to differentiate between read, write, and execute? And then what prevents you from faking that? Well, in the page fault handler, like I said, you have the faulting virtual address and you have the instruction pointer, the saved instruction pointer where the fault occurred. The only situation is if you're trying to execute code, you're going to have the faulting address equal to the instruction pointer. So that will let you know in the page fault handler that you're dealing with an execution rather than a read-write. Other questions? Yes?
If you're trying to write from a memory scanner, aren't you actually going to need to save a copy of the page before you modify it from the scanner to look at?
Yes. And that's indeed what happens.
Read the question.
So I thought zeros instead of the code that I was expecting to see when I was reading whatever page.
He's saying if you're going to repeat your question again.
Assuming that I'm some kind of AV scanner and I'm expecting to be reading bits of the kernel and I'm suddenly reading a code where I'm expecting to be able to learn code.
Oh, yes.
I need to save a bunch of
Correct. You're saying it. You know, if you're some kind of a memory scanner and you're reading, if you're expecting to be reading the kernel and it's getting deflected off to a page that just has zeros, then obviously that's abnormal. But what he's saying is you would just save a copy of the unmodified page before you actually install your hooks, and then you would use the unmodified page as a clean version. This little demo that I gave is only the most simplistic case of just hiding, you know, a few bytes in the PE header on a rootkit driver. Question? Currently, no. I have not addressed that right now in the proof of concept implementation. Question?
Isn't it, you said that you could attempt to obfuscate the page fault handler itself through monomorphism, but how would you, if you're still not hiding the fact that it can change, how would you, I mean, the huge problem is that if you're looking for changes in key components of the system, you're going to notice that your page fault handler is no longer what it used to be.
His question is, if you're how are you going to hide the page fault handler? Because the page fault handler is going to, he says, is going to be different once you have the hook installed. Well, the OS page fault handler has not been changed at all. I mean, you can integrity check the OS page fault handler as much as you want, because I am using a new page fault handler. And it's the new hooked page fault handler that is going to, would have the polymorphism applied to it, not the OS page fault handler. But admittedly, like I said, there's issues with hiding the hook on the interrupt descriptor table, because if you opted for an inline hook where you actually modified the OS page fault handler to jump to your page fault handler, then of course what you're saying would certainly come into play. Question?
How do you guarantee that your page fault handler is going to be the one that's the first one handling the page fault?
You're right, and that's the age-old problem. I can't guarantee that. I mean, I could try to set like a debug breakpoint or something, but ultimately, I mean, that's not necessarily a solution either. So that's one problem with it. The only thing that I can say is that if someone tried to unhook the memory hook engine page fault handler and say, for example, restore the original OS page fault handler, they would bring the system right down, because the OS page fault handler has no knowledge of those pages that have been marked invalid. And so therefore the whole system would crash, and it would have no way of actually recovering that. So basically it's insidious. It can't be removed once it's put in, except for removing it itself. Question? There's going to be a lot of synchronization issues. When I do a TLB flush, I'm going to have to send some kind of a message to flush the other TLBs on the other processors. There's also an issue of having multiple interrupt descriptor tables, so there's going to have to be synchronization on accessing the hash table, which contains, you know, the data in it for on lookup for the page faults. So mostly it's a lot of synchronization issues. One last question, if there are any, and then we've got to go. We're running out of time. We'll be around afterwards to answer any questions too.
Have you done any stability testing?
Well, it depends on what you mean by stability. As far as rigorous testing, I'm not a production coder. I've just written this in my spare time, but I can say that I have left the hook engine installed, running on a system for hours at a time while I was just doing my normal business, running other applications, and it's stable. There's references as well. So I'm sorry I didn't get a chance to go over them, but in the slides that you received with Black Hat, if you want to know more, I got a lot of information from like the PAX project, and you can probably, if you're interested in this, you can read more about that. Thank you.